Yesterday, where is put out the data? Yeah, for US.
Yeah,
You didn't get
All
the
right.
you go to
Hi,
US,
everyone.
Where is the US?
sound.
if you go to US.
Okay, we'll give folks just a minute to come on. I am going to take the first part of our training today. Robbie isn't able to join for this beginning part and may have to duck off a little bit early. So please be patient with me if you're sending questions in the chat, as there aren't going to be two of us on the call to try to respond in real time throughout today's session. We have quite a bit of content to try to cover today, so we'll try to go fast and keep it somewhat high level and not too in the weeds to not overwhelm everyone. And we'll try to make sure we get a break scheduled in here to break up this big 3-hour block. Let's see, I'm seeing the little dings slow down, so I'm going to assume we've got a fair number of people on. Yeah, so thanks for joining again today. I know this is quite a lot of time, but hopefully you found yesterday's session helpful. So yesterday we covered a lot of Vensim basics, just getting things installed on our computers, understanding how to navigate around Vensim and what some of the main theories are and how input data is controlled in the model. Today, the plan is to jump right into the different sector-specific pages of the model to work through what's really happening in the guts of the code and what the model is doing in each sector and how that all fits together. So today we're going to cover the 4 kind of main sectors of our model: industry, buildings, transportation, and the electricity sector. Tomorrow, we're going to cover a few of the smaller sectors or modules that we have included, like carbon capture and sequestration, hydrogen production, our land use sector, and then the input-output model as well. So there will be a few places today where outputs from the input-output model or some of those other sectors, like the CCS, carbon capture and sequestration module, come up, and I might just kind of skip over those, saying that we're going to come back to these tomorrow to see how they all fit into the bigger picture. So with that, unless anyone has any questions kind of lingering remaining from yesterday, I think we might just hop right in. Anyone have anything before we start that you think we should circle back on from yesterday?
No.
All right. Well, let me go ahead and share my screen then and bring up Vensim. Oh, a couple more people to admit here. All right. So welcome for a couple of you that just joined. We just did a very brief recap of what we covered yesterday and are going to jump right into the first sector of the model that we're going to walk through today. I think we'll start with industry. So as I mentioned, we're going to cover the main 3 demand sectors: industry, buildings, transportation, and then electricity. So you remember, to navigate between all the different pages of the model, you can click down here in the structural overview section. And then we have a whole list of pages. For each of these main 4 pages that we're going to cover today, we have 3 tabs. One is called main, one is called BAU, and one is called cash flow. So I'm going to focus on the main version of these pages today. So we're going to hop to industry main. But essentially, this is looking at all the calculations in the policy case that you're calculating. So if you have policies turned on in your scenario, this main page is going to account for all the impacts of that. The BAU is independently tracking that same calculation flow, but in a business as usual scenario with no policies enabled. And so in the end, when we can look at changes to emissions, we're just looking at the difference between the impacts calculated on this main page versus the BAU page. And then the cash flow version of the sheet is tracking the costs of all those policies. And we'll come back to those cash flow pieces tomorrow. So I'm going to click into the industry main page. And generally in these pages, as we mentioned yesterday, calculation flows go from left to right. And there are little sections of calculations blocked off with these blue bars that try to, at a high level, explain what's happening in each section. So just looking high level at industry before we jump into the details, as we move from left to right, you can see a few different blue blocks that are looking at changes in production for different industries. So this part is going to feed into looking at carbon tax effects on expenditures. Going to feed into this part where we're calculating the change in imports and production for non-fuel industries. So we're going to look at production in two pieces, one for non-fuel industries or the bulk of manufacturing, and then one for fuel industries, because this is an energy model and we have a pretty detailed calculation of fuel demand. So here we're calculating changes in imports and production for non-fuel industries. After that, that allows us to calculate changes in exports and domestic consumption for those industries. Then we're looking at production for the fuel industries specifically. Once we know how much all these different industries are producing, we can look at changes in fuel use. So we have emissions in industry kind of falling into two big categories: emissions from consumption of fuels, and then process emissions. So by industrial process emissions, we mean emissions that don't come from the burning of fossil fuels, but from other industrial processes, such as the CO2 that's produced through chemical reactions when making cement. Or this industry sector is also covering agriculture. So methane emitted from livestock are a couple examples of what might fall into this process emissions bucket. Sum up total fuel use after looking at those changes induced by policy, and then putting it all together at the end, calculating emissions. So I'm going to go through this kind of piece by piece. But that's generally, if you click into a page, you can kind of use these blue bars to orient yourself and find the what section of the code you want to be looking at. So not all of these I'm going to go into in super fine detail because it's not really necessary for me to step through every single box. Don't think we could cover everything in 3 hours if we tried to do it that way. But this whole section here that's looking at changes in imports and production for different industries is really influenced by the prices of industrial goods and how that might be changing due to policies. So this here is just summing up from some of the cash flow pieces on other pages, what the changes in prices are due to the carbon tax specifically. So this is just kind of pre-calculating an input that we're going to need in this next section of code, looking at the carbon tax effects on expenditures for industry that can be passed through to buyers. So what that means is if there's a carbon tax enabled in this policy that results in additional costs for industries, they can pass through those costs to buyers by raising the price of their goods. And so that change in the price of industrial goods is going to affect what the demand is for those goods. So that's kind of the whole concept behind this big chunk of code here for calculating change in imports and production for non-fuel industries. I should back up a step and say in this current version of the model that we're looking at for the US, we have 25 different industry categories that span a range of fuel industries like oil and gas production and coal mining, as well as non-fuel industries. So we have these broken up into many of the big categories like iron and steel, cement, and so on. We've got 25 in total, so we have a pretty broad coverage of the industry sector. So how we go about starting this is reading in output by year. And output is another word for industrial production in dollars of goods produced by ISIC code. We'll come back to ISIC code tomorrow. That's terminology used in the input-output model. ISIC code, I believe, stands for Industrial Standard, International Standard Industrial Classification Code. I maybe got that wrong, but it's just a numerical way of coding different categories of industry, and those kind of overlap with those 25 industry categories that we track in this section. So we know the amount of production of each industry. From our cash flow pages, we're reading in the change in expenses that are passed through to buyers. So that's basically any cost that industries are incurring based on policies. So that might be from the carbon tax, like we looked at before. There might be a standard like industrial energy efficiency standards or standards to install electric boilers, for example. And those are going to put costs onto industry. They can pass that through to buyers by raising the cost of their goods, and that's going to affect demand. So we read in some input data on what's called import-export substitution elasticities. You may have also heard these referred to as Armington elasticities if you're familiar with this topic. But this looks at the impact that a change in the cost of a good has on imports and production and exports. So if the cost of domestic goods goes up, we probably expect there to be greater demand for imported goods that might be cheaper relative to those higher domestic costs. We have a couple policies that can affect this as well. So in addition to just letting the model determine changes in production and imports and exports based on costs, there might be some policies that impact this. Like this is a buy-in region policy that basically you can specify that for certain categories of industry, we're going to have more domestic procurement. This might be like from a government buy clean program for cement and iron and steel. So this would raise the share of domestic production versus imported goods. And we also have, this is a new feature we added, carbon tax border adjustment that we can put on. So this would adjust the price of imported goods for their carbon content as well. So if you put on a carbon tax domestically, you might also want to put on a carbon tax border adjustment so that domestic goods aren't at a competitive disadvantage. So basically this section of code is accounting for all those shifts due to the prices of industrial goods changing and these import-export policies that might impact that. And the next step is to apply one more elasticity, which is the elasticity of demand for industrial products. So in addition to shifting whether products are produced domestically versus imported, if the cost of goods goes up, you might see a decrease in demand overall for those products. People just want less of that product because it's more expensive. Or conversely, if prices go down, people might want more of that product and you would see a greater demand for industrial production. So that's accounted for here. I'm going to skip over where we see these green control levers for macroeconomic feedback loops. Today, we're going to see these pop up in the different sectors that we cover. This is really feeding back in the outputs from the input-output model into the main demand sectors. So accounting for if you have indirect and induced changes in the economy from the input-output model, feeding it back in. We're going to come back and revisit this tomorrow. But just to note, this is where it happens in the industry sector when we're looking at changes in production. And then we have two other policies down here that can directly affect production of certain industrial goods. One is this percent reduction in non-energy industry product demand this year. So you can think of this as investments in things like material efficiency and recycling. So that would require less of certain products like cement or iron and steel. So you can just kind of read in a percent change in demand for certain industries based on those types of policies. And we also have one that specifically influences our agriculture sector. That is one of our 25 industrial categories, is agriculture. And this is shifting from animal products to non-animal products. And we have some input data that helps us calculate if we were to reduce animal products by a certain percentage, how much additional agricultural land would we need to devote to plants to make up for those lost calories, for example. So that all leads us, summing this all up, we can see we've highlighted this gray as an important intermediate output, the percent change in non-fuel production due to policies. The next couple blocks, the next block here is now that we calculated the changes in production and the changes in imports, we can also do the same for exports and domestic consumption. So we have those elasticities of imports, exports, those Armington elasticities that I mentioned earlier are input data that we read in. That can allow us to calculate the change in exports of non-energy products. And once we know that, we can just do some simple algebra to say that consumption of any given good is domestic production plus imports minus exports. So all those things balance, and we can report out graphs of production, imports, exports, and consumption, which is a cool new feature that we added in recently. We do a similar set of calculations for the fuel industries specifically. We do this separately because it's a bit more complicated than some of the other industries, because as you can imagine, many of our policies affect the demand for fuels in our model. If you're decarbonizing the electricity sector or the transportation sector, that's going to affect the demand for different fuels. And that's calculated for here. I won't go into too much detail because some of this is happening on the fuels sheet, which I think we're going to visit tomorrow. But based on those changes in demand from different sectors, and some input data we have on typically what fuels, how much is exported, and how the demand for exports and production has changed historically. We can calculate what the percent change in production due to our policies is for each of the fuels that we track in the model. So that is all just tracking our changes in domestic production, because we want to track what the emissions are from domestic production of goods. So now that we've done all that, we can move to our first of our big two categories of emissions, which is emissions from fuel use. So there are many different policies that we can turn on that affect fuel use in the model, and those are all denoted by these blue boxes here. And as we turn all of these on and off, essentially what we're doing is just calculating a percentage change in industrial fuel use relative to BAU. And we're doing it this way because instead of tracking individual pieces of equipment in the industry sector, like every industrial boiler that's in the economy, what we're doing is we're reading in the demand for industrial energy consumption with this input data file here. I think we actually opened this up as an example file yesterday, but this is the BAU industrial fuel use before CCS. This is one of the most important input data variables for the industry sector. In the US, we're taking this straight from EIA's annual energy outlook, but we have for each of the 25 different industry categories, the consumption of each of the 10 fuel types we track in terms of BTUs in the BAU case. Then we have these blue policies. So this includes, I mentioned yesterday, we have a series of research and development policies where you can kind of test, okay, if through a research and development program, we increase the efficiency of industrial equipment, what might that impact be on industrial fuel use? We have a couple policies that use some historical data from various academic studies on what the impact would be from programs like retiring the most inefficient industrial facilities early, addressing some installation and system integration issues, applying more cogeneration and waste heat technologies. And then finally, we can look at industrial energy efficiency standards, and you can apply these at for each of the 25 different industries separately. So adding all of those up, you can calculate the percentage change in industrial fuel use, and then apply that to find the changes relative to BAU. One other important piece of input data here is that we want to separately track fuels that are used for energy purposes, so combusted to provide energy, versus fuels that are used as feedstocks, such as petrochemicals that might be used in the plastics industry. So we subtract out fuels that are used for feedstocks, and that gives us the fuel used for energy purposes before fuel shifting. So the next set of policies that we can apply is fuel shifting. So this is a little bit different than efficiency, where we're decreasing the actual amount of fuels burned. We can also shift fuels, such as looking at electrification for certain industries, or for certain high heat processes. There's a lot of interest in using hydrogen in the industry sector. Kind of to get at this fact that hydrogen is often targeted for certain high heat processes that are going to be difficult to electrify, we split this fuel use into low temperature heat needs and medium and high temperature heat needs. So we have two different sets of policy levers. So the first one is fraction of low temperature industrial heat shifted to other fuels this year. So this would be looking at shifting natural gas and coal boilers, for example, to electric heat pumps. And then for medium and high temperature industrial heat, you can shift this to a combination of electricity and hydrogen, and kind of tailor that based on what you see as the potential for those technologies in different industries. And you can set that through your policy settings. So this tracks increases and decreases in the consumption of each of those fuel types based on what you're shifting. And adding that all up, you get your total industrial fuel use for energy purposes before carbon capture and sequestration and methane capture. We're going to come back to that in just a minute. That's the main part of our changes in fuel use code. Now we're going to jump over to the second main category of industrial emissions, which is process emissions. This is another, or these two here, these two purple levers here, are the two other really big and important input data pieces for the industry sector that if you're modifying the model for new region, you're definitely going to have to tailor this input data. So first is business, or actually, sorry, I was pointing to the wrong variable, not this one, and this one. So first is BAU process emissions. So we want to know in our business as usual case, what are the process emissions from all of our different industries? And then this is the potential for abatement of those process emissions. We use a central source for that has data for every country from the EPA. So by default, we have data for every country that we'd be interested in making a model for. That can, of course, be substituted if a country has their own data that they want to supply. But this source from EPA does a really good job at reporting business as usual process emissions, as well as marginal abatement cost curves for abatement potential. And that means at different cost tiers. So I think it goes by $10 increments or so. In each cost tier, how much emissions can be abated by different technologies. So this allows us to apply all of these blue policies here as a percentage of the potential that EPA sees being achieved. So if I said 100% of the potential for all these policies I want to implement in my policy package, the model is going to apply all of the potential that is listed in this PERAC variable. If I were to say only 50% of the potential was implemented, the model would implement the cheapest 50% of the potential and would leave those higher cost technologies unapplied. So just to go through what the different levers are here for process emissions, we have methane capture, and this can be applied in the oil and gas sector, in the waste sector, and in coal mining. That's for methane capture and methane destruction policies. So methane destruction meaning flaring of methane. We have 4 different policies for different technologies for addressing fluorinated gases. Those are those high global warming potential gases used in things like air conditioning. So you can address these by substituting different gases that don't have as high global warming potential, for example. We have 2 categories of agricultural process emissions policies, one to address croplands and rice. Actually, no, I think we have 3, sorry, croplands and rice, the methane and N2O that comes from those. One to address livestock. This is mostly methane that comes from ruminant animals like cows. And then CO2 storage through tillage practices. So this is sequestering CO2 in agricultural soils. We also have cement measures. This is practices like using different cement clinker chemistries to reduce the amount of CO2 that's produced when you're manufacturing cement. And then N2O abatement. This is a pretty small lever, but applies to some technologies you can apply to the chemicals sector to cut down on N2O emissions there. So basically, based on what settings, how much of the potential you want to apply, the model will sum up how much abatement you can achieve for each of the sectors based on how much potential you have in this input data file. And you can calculate a change relative to the BAU process emissions based on that. This little section here is just accounting for the emissions from that animal product shifting lever that I mentioned before. So accounting for lower share of livestock and higher share of crops if you choose to use that lever. And this is just kind of tracking it through, coming up with this percent or sorry, also accounting for the fact that you might have a percent change in production due to policies that we calculated earlier, you can come up with the total change in process emissions as a result of all these policies. All right, so we've made it most of the way through industry. Now it's kind of just putting things together and summing them up. So we want to calculate total fuel use first before we can get to emissions. So we looked at the changes in fuel use earlier. We just want to add in a couple things. One is any fuels that are used to power carbon capture and sequestration equipment for the industrial sector. This is going to be in our separate CCS page that we're going to cover tomorrow. So you can see this is a shadow variable that's italicized because it's being read in from a different section of the model. And then also any methane that we captured from that methane capture policy in the process emissions section can offset some natural gas use in the industry sector. And so we just account for that here. So we sum up all of the fuels that are used for energy purposes after adding in those two little components. We add in the fuel use that's for feedstock that I mentioned we separated out before. And that gives us our total industrial fuel use. And here you can see we're just splitting off, we're keeping track of what the electricity demand is for the industry sector, and we're going to read that into the electricity sector later. The last step, now that we've done all that, is just to add up what the emissions are. So we have our industrial fuel use for purposes, for energy purposes. We're adding in that bit from CCS. We're accounting for our process emissions, which we calculated earlier. And then we have for the portion of fuel that is burned for energy, we have pollutant emissions intensities. We track those for every fuel and for every sector. So given the fuel consumption, multiply that by the pollutant emissions intensities, that's what gives us our total emissions. And yeah, that's kind of just adding it all up here. And these orange coloring, if you remember, are important output variables. So this is just, if you're coming to the industry page, you can kind of easily spot these final important pieces of the calculation flow that you might want to pull out and export to report outside the model. So I realize we went through that pretty fast, but seemed to be actually pretty on time for the agenda. So we've got a little bit of time to pause here for questions before moving on to another sector.
Yeah, thanks very much,
in the
Megan.
chat.
That was really interesting. I just had this question about feedstocks and how they're treated.
So the fuel shifting portion, where we're looking at electrification or hydrogen use, is only impacting the fuels that are used for energy purposes. It's not looking at feedstocks. We have a few ideas for how we might improve the industry sector in a future version of the model, and we want to add in a few more policies that are tailored towards decarbonizing feedstocks. But right now, we don't really have that. And the way that you would see changes in the amount of feedstocks is really just if you're seeing changes in the amount of production for a given industry.
Okay, perfect. Thank you.
Megan,
Yes.
we've got two questions here. I'll go first, which is, can you talk about any time constants that are in the model? For instance, just like process adoption of technologies throughout industry. I know you have those fractions of the potential achieved this year. And I assume that fraction is defined in the policy implementation schedule, but if I just say all of the, cropland and rice, like, I don't know. Anyway, pick one of those cement. So I just say, hey, next year we're going to equal 100% of that cement. Is there any other time constants preventing an overnight adoption?
Yeah, so that really is, well, there's kind of two things that influence that. One is, of course, the input data for how much potential you say there is in every year. Generally, from the EPA report that we're looking at, you see a gradual increase in abatement potential with time as you have new technologies coming onto the market. But an important part of that as well is the policy implementation schedule. So there's nothing blocking you in the model from saying next year we're suddenly going to go and implement 100% of what EPA says the potential is next year. That's more of a user judgment for how you want to phase that in. But you do see in input data that we're using EPA accounting for the fact that as new technologies come on the market, that potential abatement is going to keep growing.
Great. And we have one more question.
Yeah.
Okay. Megan, I just want to ask you one question on land use and how do you calculate cook stove? I didn't see how you are capturing the cook stoves because in Africa, people using highly cook stoves.
Oh, cooking stoves.
Yeah,
that's
how do you capture it? And also crops as well. I see you have livestock. Did you decide to get livestock as well, or?
Sorry, it's a little hard for me to hear you. Can you repeat that second part of the question?
So the two questions I think were how emissions from cook stoves, how are those handled? And I think the second question was, is livestock disaggregated by species?
Okay, so first for cook stoves, so cooking stoves are actually going to be tracked in the building sector as a building appliance. But in terms of linking the land sector to demand for biofuels, we don't have that linkage really set up right now in the model. It's something that we have pegged for one of the next updates, is to better link as you see demand for biomass or liquid biofuels in the transportation sector change as a result of policies, linking that back to production of agricultural lands. That is not something we have built in at the moment. For part two, for livestock, we don't explicitly have it broken out into different species, but in the input data that we use over here, we do kind of account for the production of different types of agricultural products and different species of livestock for these two pieces here. The ratio of nutritionally equivalent plant to animal products produced per unit land area, nice and simple variable name there, accounts for some of those things in the input data.
Thank you.
Other questions on industry? We also, I don't know that we pointed this out yesterday. I should mention online on our documentation page. So if you're in the model and you go to view the online guide, you can pull up our documentation page. We have a lot of documentation here, including here under model component descriptions, some guidance on what's going on in each sector. So this will kind of walk through the main components of what we just discussed with some screenshots and some discussion of what's happening. This is a good place to refer back to if you want to refresh yourself. The main caveat is that some of this guidance is fairly outdated, so it's not up to date with the newest model platforms. We're going to try to be continuously updating these a bit more than we have in the past to bring these up to date, but still a useful place to come kind of as a refresher for some of what's happening in these different model sectors. All right. We're actually on the agenda. We had until 2:45 Eastern blocked for industry, so we're kind of right on time. So unless anyone has any other pressing questions on industry, I think I will shift us over to our next section, which is the building sector. All right. So building sector, not quite as much going on as in the industry sector. So I think we can get through this a little bit faster. But similar to industry, for buildings, we are taking in energy service demand from an external source, and we're not tracking individual pieces of equipment. So we are not tracking the number of heat pumps or the number of ACs in the building sector. We're tracking overall energy demand by building type and by building fuel and by building component. So for the building sector, this is probably our single most important piece of input data, this BAU components energy use. And I think we showed that file yesterday. So we're tracking energy use across 3 different building types, urban residential, rural residential, and commercial buildings for, I believe, 10 different fuels within the building sector, and then 6 different end uses. We have heating equipment, cooling, appliances, lighting, an other component for other types of appliances not captured in the other categories, and then finally a building envelope category, which doesn't consume fuel on its own, but if you improve the efficiency of the thermal envelopes of buildings, that can cut down on heating and cooling costs. So we're reading in all our input data on components energy use in the business as usual case. And the first thing we want to do is to understand what fraction of that energy use is from newly sold components in this time step. So we have this piece of input data, share of components energy use that is new this year. That is for the most part just 1 divided by the average lifetime of a building component. So if you sell a new piece of heating equipment or the average lifetime is 20 years, about 1/20th of the demand for heating is from newly sold components in this year. And you'll see why we want to separate out the newly sold component based on the types of policies we're going to start applying. So all these blue boxes here are policies that you can apply. And like in the industrial fuel use section of the calculations that we just went through, we're going to apply these all as percent changes in demand. So first policy you might apply is a component efficiency standard. So efficiency standards for newly sold appliances. So you can say newly sold air conditioners must be 10% more efficient this year, or so on. You can calculate how that affects new components demand. We also have these research and development policies, so you can test, okay, what would happen if through research and development we improve the efficiency of new components. We have a couple other policies that again use some academic literature to look at historical impacts and how similar programs might affect energy use. So one might be the effects if you improve contractor education and training. And another might be if you have improved labeling, such as Energy Star ratings on your appliances. How might that affect the energy efficiency of newly sold components? We're going to just keep moving to the right through this calculation flow as we apply more and more policies. Another one, again, using some historical data on similar programs is a rebate program for efficient components. And you can look at how that would affect the market share of different types of appliances of different efficiency levels. Factor that into the calculation here. We also are going to account for elasticity of component energy demand with respect to energy costs. So we are tracking on our fuels page, which we're going to come back to tomorrow, the costs of different fuels and how those might be influenced by policy. So if you have a change in the cost of natural gas, for example, that is going to affect the demand for natural gas usage in buildings. And so we account for that here. And then again, like we saw in the industry sector, we now have a section for fuel shifting of components. So this is a policy lever for a fraction of new building components shifted to other fuels this year. You can think of this as an electrification standard. So you can say, okay, X percentage of newly sold heaters this year must be electric rather than natural gas. And just important to highlight again, this is when we're talking about newly sold components, this means all heaters sold either to replace old equipment in pre-existing buildings. So for people that have their heating equipment die and need to replace that, as well as heaters in newly constructed buildings. So this is capturing all new sales of building equipment. And then finally, the last thing here is applying envelope effects. So this is just if you set an efficiency standard or an improvement in the building envelope, for example, so making sure that new homes are constructed to be more thermally efficient. That's kind of added into the calculation flow right here at the end. So we have new components, potential energy use after envelope effects. So that's our first tier of the calculations. And now we can move down to kind of putting it all together and looking at total energy demand in buildings rather than just the demand from new components. So here is one of these stock and flow calculations. We mentioned yesterday that when you see a variable in a black box here, that's denoting that there's some stock and flow tracking happening in Benson. So above, we just calculated what the demand is from new components. We know the average lifetime of different building components, so we can calculate what the retiring components energy use is. And then since we're tracking energy use in each time step, we know what last year's was. And if we add last year's energy use plus the new energy use minus the retiring energy use, that gives us this year energy use. We need to account for a few more things. First is price demand feedback. So similar to what we were looking at above, accounting for an elasticity of service demand with respect to energy costs. So again, if natural gas costs are going up, you're going to see people responding to that by changing their demand for fuel use in buildings. There's a little bit of code over here. I won't go into detail. Essentially, what this is doing is adjusting for the fact that to apply this elasticity, you need to calculate the percentage change in fuel costs for buildings. And the calculation gets a little messy if you don't account for the fact that you might have a fuel shifting cost that really changes the demand for building fuels in your policy case, but not in your BAU case. So this is kind of coming up with a hypothetical BAU if you had applied fuel shifting. So we're comparing the change in energy cost in the BAU versus the policy case on an apples to apples basis. And that allows us to calculate a percentage change in all components energy use due to price demand feedbacks. The next step is to apply those macroeconomic feedback loops, which again, I mentioned we're going to cover this in the input-output model tomorrow. And so we'll kind of revisit what this is. It'll make more sense once we cover that first before covering how it gets fed back in to the main demand sectors of the model. And the next step is to account for the effects of one other policy, which is retrofitting pre-existing buildings. So most of the policy options in the building sector, which we covered above, are affecting energy use from newly sold components. Retrofitting is one example where we're looking at going into pre-existing buildings. So let me actually just jump over here to where the retrofitting is calculated. It's a pretty simple section of the code. We implement this policy as the share of pre-existing buildings subject to retrofitting to date. And we have some data from some historical sources on what the energy savings that have been achieved by other retrofitting programs have been in the past. So what the impacts on heating and cooling demand of retrofit buildings might be. And we're applying this to the share of pre-existing buildings. So we have our average lifetime of buildings. We can calculate then what share of buildings that existed in the start year are still surviving in any given year of the model run, and kind of apply it that way. And that gives us a % reduction in energy demand due to retrofitting. So that is that same gray variable that shows up here. We just subtract that energy use from retrofits out of the total. This is just kind of now summing everything up. We have a couple correction factors, and we get total building components energy use. I'll just mention this green control lever variable in case you're wondering what this is. We're not currently using this in the US version of the model, but we have a control lever set up to account for the impacts of COVID for regions where they might not have up-to-date information on energy demand in the year 2020. So if you're using a data source that doesn't account for COVID because it was compiled before 2020, you can kind of feed in the percentage change in energy demand due to the drop in GDP from COVID. So again, we're not using this in the US, but when you see these green control levers throughout the demand sectors of the model, this is just where we have kind of some code built in to account for COVID. Again, we track the pollutant emissions intensities of different fuels. So we have the pollutant emissions intensities for the building sector, which can give us direct buildings pollutant emissions. Sum those all up, and these are kind of our orange output important variables for emissions of all the 12 different pollutants in the building sector. There's just one other section of the building sector to cover in addition to emissions, and that is distributed solar. So that's this last section over here. So to cover that quickly, we have input data on the amount of distributed electricity capacity that we have in the BAU case. And then we have two different policies that can affect distributed solar. One is a subsidy for distributed solar PV, and we pair that with an elasticity of distributed solar deployment. So looking in the past, what the response has been in terms of deployment, if you have a subsidy, we can calculate what the newly incentivized capacity due to policy would be. And then we also have a a carve out, so a minimum fraction of total electricity demand that needs to be met by distributed solar PV this year. So if you know the capacity factor of distributed solar and the minimum amount you want to meet, you can calculate the amount of capacity that is deployed due to this policy. And then kind of add it all together and track it up here. We can look at the cumulative impacts of how much new solar, distributed solar capacity we have due to policy. Then there's just this one last little section of code, which is comparing that change in distributed solar capacity to BAU and looking at what the change in output might be. And then making sure that we are subtracting out any electricity generation that is now met by distributed solar from the net electricity demand that we're going to feed into the electricity sector. So distributed solar is really covered here in the building sector rather than the electricity sector, and we subtract that out before feeding in our electricity demand. And I think that is pretty much it for covering the building sector. That went fairly fast, just because the building sector right now is probably the least complicated of our 4 main sectors. We do have, I'll note, a big building sector overhaul in mind for a future update, where we will move away from using this variable that reads in overall energy demand and track from a more bottom-up level where we are tracking individual pieces of equipment, and that would allow us to have a little bit more flexibility in the types of policies that we have in the building sector in a more detailed way to track that. But for now, this is how the building sector works. So I will pause here and again take any questions you all may have.
I think
A
Was that
question,
a
Megan,
question?
can you hear me?
Oh yeah,
Yeah, I see you have included training and labeling for any, possible energy change. But how about if there is behavioral change from bottom up? If the people change their consumption patterns, is there any way that you can calculate it here? I see the training and labeling are top down, kind of from top down approach, but
so I think one
people
piece
change
of that
their-
is the elasticity of service demand with respect to cost. So as the cost
Okay.
of fuel changes, people will, if fuel costs are going up, they'll decrease their demand, or if fuel costs are going down, they might increase their demand. So that's one aspect of the consumer behavior and how we capture that there.
Okay, gotcha.
I have one.
A little bit of feedback going on there.
Are you muted? Okay, go ahead.
I'm so sorry. I have a minor question about the brackets. I don't know when we use brackets for text, and what does it mean to have Boolean in the text?
I think the
So
green variable could be an example of what she's asking about.
yeah, Boolean. So the term Boolean is just like an on-off, yes, no. So again, we're going to come back to these macroeconomic feedback loops, but basically, if you have a control lever that says Boolean, this just means, do I want to disable macroeconomic feedback loops, or do I want to keep them on? It's just like a yes, no lever that you can toggle on and off to control model behavior. So a lot of these green control levers, you'll see Boolean because it's kind of a yes, no option for whether you want to choose one set of default model behavior or another. And I think you were asking about like what the little carrots mean. Was that your other part of the question?
Yeah.
Yeah. So that is referring to something read in from another page. So, yeah, shadow variable. It's a shortcut to something calculated elsewhere in the model. So here you can see, where we're newly calculating a variable, we don't have those little carets, but where it's being read in from either an earlier part of the calculation flow or a different page of the model, that's where you see those little inequality signs or brackets, just kind of useful notation for us to keep track of where things are coming from. One little trick that I don't think we mentioned yesterday that I find very helpful, if you have this move size button on the toolbar selected and then you click on a variable, so maybe I click on this and I want to say, where is this actually originally being calculated in the model? And then I hit F3, the model's going to take me to all the other occurrences of this model. So this is another shadow variable pointer. That's a shadow variable. Where is it being originally? Oh, here it is. So this is the building's fuel cost per unit energy is being calculated on the fuel page. You don't see the brackets here because this is where the first instance of this calculation is done.
Thank you.
Yeah, any other questions?
Hi, this is Travis. The solar, I mean, I guess in some ways could be calculated in the energy sector and then just be energy subtracted, with the shadow variable, like you just said. But is the structure of the distributed solar very similar to the structure of any other energy source? We're about to look at it, but maybe I'll just ask the question here.
Yeah, you'll see the electricity sector is quite a bit more complicated than distributed solar. For other utility scale power plant types, the model is going to choose which resources to build and dispatch based on cost, whereas for distributed solar, we're kind of just applying these pretty separate types of policy levers, which I think is why we break it out and fit in this different section of the model. But I think that'll be a little clearer once we walk through the electricity sector.
Thanks.
All right, any others?
Can I ask a question about land use considerations?
Sure.
Are there any limitations to how building can happen? And the reason this comes up for me is the distributed solar question, whether there's any competition for land, or is that considered?
No, we don't have that type of feedback built in. As I mentioned, we don't have very many linkages between other sectors of our model and the land use sector. It's something we're maybe looking at in the future, but no, we don't have any of those limitations in. All right. Let's see. I know Robbie was going to come back on for a little bit and maybe take over some of the next section. But maybe this is a good time for a break if Robbie is not here yet. Robbie, are you on? All right. I'm going to say, rather than kind of start into a new section right away, since Robbie was going to take part of that, why don't we take a 5-minute break? So come back around 3:10 or just a little bit after. Give everyone a second to take a bio break. I will see you all back here shortly.
Hey, Megan.
Yes.
Just like, so one of the last things we were getting out the door, I was getting out the door at Climate Interactive was land use connections with demand and, energy supply and bioenergy and agriculture and livestock and stuff. So if you they'd be a good resource if you want to talk about how they've approached making all the
Yeah, that's
connections
great.
between. Because our big goal was to only use each hectare once, and not try to, because I think there's a lot of double counting that happens when people are kind of like doing some other levels of analysis.
No, thanks for that flag. That definitely sounds useful, and we might want to circle back.
Okay.
All right, I'm going to go off camera here for just a minute and be back soon. All right, everyone. I think Robbie is going to be joining in just a minute and is going to take over for starting off our electricity sector. I'm just going to give him a second to join while everyone else is still regathering. All right, I think that's Robbie just joined.
It is.
All right, we're just kind of getting back from break just in time for, if you wanted to kick us off for the electricity sector.
Oh, great. Happy to do it. I will have to leave in about 30 minutes, but happy to do that. Okay. Okay, so flip over to the electricity sector. So let me start with the BAU actually, and just zoom out, and we'll do kind of like a quick walkthrough of what's going on in each piece, and then we can dive in a bit more detail. So this is just the BAU case. So the first thing we do is we determine the total. So before I start, two comments. So one is just a note that we are in the middle of completely redesigning the electricity sector and the EPS, which will be done in version 3.5 sometime, hopefully within the next few months. And there's a couple of key things that are being done there to really improve the capabilities of the sector. So one is that the model is an annual model, and right now the electricity sector just runs on kind of an annual average basis. But in the new version, we'll actually have hourly dispatch. So we'll have much more granularity in the model, and we'll be able to do a much better job handling reliability related concerns and the performance of different resources as the system decarbonizes much better. The other key difference is the current version of the EPS builds to meet total annual energy demand, as well as other policies that are required. And then there's a mechanism to make sure there's sufficient capacity to meet peak demand. But what it doesn't do is deploy resources just based on economics. So if something comes along and gets an incentive, like solar or wind, if there's not another policy like a clean electricity standard, and there's flat or declining electricity demand, the model isn't going to decide to build that just because it's economic. And we know that that's not reflective of the way that sector works. For example, if you look at the tax credits from the US Inflation Reduction Act, a lot of those are just meant to make solar and wind cheaper and to entice developers to build those resources, even if they're not needed for demand. So the new model will have that new granularity at the hourly level, and it will also be able to handle both those reliability-based additions to meet annual electricity demand and peak electricity demand. And it will also have a component that allows the model to build to meet, or it will build new resources if they are economic. And the more economic they are, the more of them will be built. And then finally, the other thing it does is right now we kind of have a lumped total of power plants. So we have kind of the entire power plant fleet by power plant type. The new model introduces vintaging, so it tracks power plants in every year. And so that gives us a lot more granularity into the performance and retirement of different power plants. So we can do another training on that when it's complete. However, given that this is the existing structure and that all of the current models and for the foreseeable future, most of the existing models will continue to be on this platform, we thought it would be a good idea to still do kind of an in-depth dive here on kind of how this works, and then supplement that with another training on the updated power sector in the future as needed. Eob asked when those are expected to be done. The hope is to have those done sometime in the next couple months. We have some folks who will be out of the office, including Megan, for an extended period this fall, and another colleague, Jeff, who's taking part of his well-earned sabbatical. So the timing is a little bit in flux, but we have kind of a working version now, and we're calibrating it and customizing it. So it's kind of just a matter of time until we finalize that.
Robbie, why given the kind of what we talked about yesterday with investment budget function, why would, if you had a solar incentive from the IRA, why wouldn't it cause more solar to be deployed in the current structure?
Because the current structure only allocates new resources if there's new demand. And so, I mean, we can start walking through and you'll see what I mean here. So the model,
But new energy demand, like I guess in most scenarios, doesn't energy demand go up even if emissions is going down?
depends. Actually, the US has pretty flat electricity demand growth. Even, I mean, if you look at electrification, that's different. But you know, you could have relatively flat or even decreasing load growth, say from efficiency. And if you have enough capacity in the power sector, then there wouldn't be kind of net new demand required that the model would be building to meet. So the most like dedicated power sector models, they're called capacity expansion models, and they function quite a bit differently, and they're just trying to minimize the total system costs. And so if you have something that's really cheap and can minimize the total system cost over the time horizon, it will build it. Ours is going to be something in between because it's not designed to be a kind of a cost minimizing capacity expansion model. So what we're probably going to end up doing is looking at individual technologies and how profitable they are based on when they run and what market prices are. And then we'll have an elasticity function that will relate the profitability of power plants to how much gets built. And then as more of those resources get built, they'll become less profitable because they won't run as much in certain hours and prices will come down. So we expect that it will be a good kind of hybrid approach to projecting cost-based additions.
Yeah, that makes sense. And so if we just take two energy sources today, if solar were cheaper, and it might be only added as, like, say, coal is retired, if we just have those two energy sources in the grid. So if we had flat demand, as coal plants retired, it would get replaced with the cheap, like most likely, you know, the cheaper energy source.
Exactly, right, without any policies. That's right.
Yep.
Yeah. Okay, so I actually will just jump into the main section here, and we can kind of walk through what's going on. So the general theory here is the model determines how much demand there is, and then so it determines the energy need. Then it starts layering on some policies. So we have a mandated capacity construction policy we'll talk about. We have renewable portfolio standards. These also include clean electricity standards. And then we have some residual amount of demand here. The model then does an allocation, again, using the logit function that we've talked about to allocate new resources to different types of technologies. Then it does a check to make sure that after it's allocated things just based on essentially a levelized cost of energy, that it has sufficient supply to meet peak demand. Because sometimes if you just do things based on the levelized costs, especially if you have a lot of variable renewables that aren't dispatchable, you may not be able to meet peak demand. So the model does a check to make sure it can meet peak demand, and if it can't, it will add more resources flagged as peaking resources. So those tend to be things like natural gas and oil-based peakers. And so that's what this whole section is doing here. And then at the end of that, we've got kind of the total net capacity that's been added to the system. If we go down a level, that's where some of the costs and things that feed into that are handled. So this section here, calculating annualized cost per unit output for new capacity. This is essentially where the levelized cost of energy is calculated. Next to that, we have calculations of dispatch costs, which are variable fuel and O&M costs. And then we have what we would call going forward costs, which are fuel variable, O&M, and fixed O&M costs. And this is used elsewhere to help, for example, decide on economic retirement of power plants. So that feeds right in here. So this is capacity retired early for economic reasons. We'll talk about how the model decides on other retirements as well. And then this is a stock and flow part of the model where we're tracking capacity. Now there's a whole interesting system here to track reliability and flexibility of the power system, which we'll jump into some more. But at a high level here, this is just, this is the flexibility points system that helps us manage kind of how much renewables can be added and what the curtailment rate is. So once we've calculated prices for different technologies, we've built to meet demand if needed, or peaking or capacity or other policies, and then we've tracked the whole set of power plants here. The next thing is to then figure out what gets dispatched. There's two dispatch mechanisms in the model. There's a guaranteed dispatch mechanism and there's a least cost dispatch mechanism. Guaranteed dispatch guarantees at least some minimum amount of dispatch to different power plant types. The best way to think about this is kind of like what has historically happened in China, where power plants get allocated a certain number of hours per year that they will run at minimum. And then anything residual goes into the market to be done economically. This can be turned on or off in the model, depending on whether or not you want to use it. The one caveat is peaker plants by default in this older version of the model, they get guaranteed dispatch in order to make sure that they run at the capacity factors we expect. We then have a least cost dispatch mechanism where the model will dispatch power plants based on whatever is most economic on the system. And then from there, this last part is basically aggregating generation and emissions, some interesting additional outputs. And then I need to open, I have a different version of the model open. And then from there, we have a few graphs that help us track capacity and generation. Let me, this is the wrong model. So let me stop and open the correct one here. Okay. So starting at the top left, the model first takes in total electricity demand. So this is the sum of all of the electricity demand in the other sectors, inclusive of policy-driven changes in electricity demand. It then accounts for transmission and distribution losses. So somewhere usually between 2 to 15% of electricity is lost on the transmission and distribution system here. That is based on input data, so it varies by country. And then that can be addressed through a policy that's specifically designed to target avoiding transmission and distribution losses. So this number is the total amount of electricity that has to be supplied to the grid before we get into imports and exports. The next step is to calculate those imports and exports. So imported and exported electricity in the BAU case are read in as input data files. Exported electricity is just a megawatt hour value. Imports can actually be specified by power plant type. So if a system is going to have more renewables be imported than say coal or gas, you can specify that in the input data. This is important for a lot of US states and provinces, which actually include imported electricity emissions as part of the inventory. Both of these can also be affected by policies, which change the amount of exported electricity in aggregate, or change the amount of imported electricity by resource type. So you can reduce the amount of coal or gas or whatever that's being imported. There's also a green thing here. Note that this is one of those feedbacks we talked about earlier. So there's a feedback here that affects the total net imports of electricity. So down here, we now account for the net imports and we adjust the total electricity demand so that we either lower the amount of demand if we have net imports, or we increase the amount of demand if we have net exports. From there, the model then goes into determining how much new output, how many new megawatt hours of supply are needed this year, to your question, Travis. And so this process looks at the total electricity generation capacity. It takes out the retiring expected capacity, and we get a total surviving amount of capacity. Now that gets multiplied by what we call our kind of average expected capacity factors. And so using that, we get what is the estimated surviving electricity output? So that's the total capacity multiplied by the expected capacity factors by power plant type. And this is an attempt to get at the fact that the model is, again, an annual model, but we're trying to look at kind of reliability on a hourly basis. We also adjust capacity factors down here, given flexibility and curtailment concerns. So using the flexibility point system, which we'll come back to, we have some equations that relate the supply of flexible resources to curtailment rates. And so this section down here is specifying up to a third order polynomial that relates the total supply of flexible resources like storage or peakers or pumped hydro to curtailment rates of different resources. And then we adjust the curtailment rates of those resources based on the total, amount of supply on the system. So for example, in the US model, we have, 1 to 6, getting all the way up to 6% in the BAU curtailment rate for solar, and then that number stays in the low 2s for wind, just kind of in the BAU. So that factors into how much can be dispatched. It also will affect later what the expected levelized cost of technologies are. So now we've got the total demand. We have kind of what's remaining this year in terms of potential output. And the difference between those two things is how much new output we need to build this year. So the next thing we do is we check to see how much output is still in demand after we have what we call mandated capacity construction. So this is meant to reflect the fact that, first of all, there are already projects in development that will be built in the early-ish years of the model. So we want to be able to reflect those. And also in some countries, the government kind of decides what will be built. It's not necessarily left to the market. And so this input data and policy lever here allow users to basically force the model to build certain resources to reflect policy or potentially kind of existing government policy. So that if you take the new capacity that's built and you multiply it by capacity factor, that gets you the new potential output from policy mandated capacity. And then that gets subtracted from the total demand that we had. So you get electricity output to allocate after mandated construction. The model then moves to the next policy, which is it's called the renewable portfolio standard in the model, but it also reflects a clean electricity standard. So to that point, you can actually you can set input data to allow or disallow certain resources from qualifying to be clean. And you can actually do that in the BAU case here, as well as the policy case, if you wanted to look at a policy that, for example, changes from an RPS to a clean electricity standard. So the model then implements whatever user setting you have. So we have a BAU renewable portfolio standard percentage, and then you can add on top of that with policies. And this section is really all about figuring out first how much additional potential output is needed to meet the RPS, and then allocating that to different technologies. Megan, did you go through the example online of the allocation, the curves?
Not yet. We only did in-stream buildings.
Okay, so let me pull that up and we'll. So just to give a rough idea of how the allocations work, I'm going to show this graphic once I pull it up. Okay, so we talked about this a bit yesterday, but we use a logit allocation to assign demand for technologies in aggregate to certain specific technologies. The logit is a function that that is kind of designed to do that, and it's based on a few factors. So it's based on the levelized price or cost of technologies. It's based on a share weight. So a share weight can control the size of a different technology, and it's based on an exponent. And the exponent determines how sensitive the model is to changes in prices. So smaller absolute values, or just, smaller absolute values for the logit exponent mean the model is less sensitive to price. And then higher absolute values mean the model is more sensitive. So a value of -1 in the exponent might get you a pretty even spread across technologies, whereas a value of -10 would push the model to basically only allocate to the cheapest technology. Functionally, the idea is something like this graphic, which this is just in the docs. So US.Energy Policy Solutions.docs, and this is the electricity sector page.
We can't, oh, there.
Okay.
Thanks.
Okay. And the idea is basically that each technology is represented by a curve, a normal distribution curve. And you could imagine in this example, we just have wind and solar, but you can imagine if we had 15 technologies, there might be 15 differently overlapping curves. And so the average price for each technology is its mean. So for wind, that would be 3, and for solar, that would be 5. The y-axis is the output buildable at unit cost. So this is, you could think of it at a cost of 4, this is how much solar could be built, and at 5, this is how much, and at 6, and so on. And then the area underneath the curves is the total available megawatt hours of that resource that are buildable. And so what the model does is it figures out the total output that's needed, and it will go ahead and start filling in the area under this total curve until the area satisfies the total amount of demand that needs to be met. So for example, if the area overlaps perfectly with where this 4 is, that means the model will build all this wind up until 4, and then just a little bit of solar as it ramps up here. So you would get a majority wind. And so as you need more and more supply, you would get a higher share of the more expensive technologies being built. So that's kind of the basic theory behind this. Since we don't have specific plant level information, we represent the technologies as these kind of resource curves. Okay, so
Robert,
yeah.
Are the resource curves different by location, by geography?
So they are, for each of the models, they differ because they are centered on the average price. So like each technology should in theory be different in terms of its levelized cost in different regions. So they should differ by region. But there's no, like since the model doesn't have, it's just a single region, there's no kind of like granularity beyond those curves. They're kind of meant to represent the geographical distribution of the resources within a single region. So the model does an allocation pass here just for the RPS. So only resources that are flagged as qualifying can get allocated. And then after it's done, so the model has now ensured that it's built enough supply to meet the RPS or Clean Electricity Standard. And now now it checks to see, okay, is there still more supply that's needed to meet demand? And if there is more supply that's needed, then it does another allocation, but this time it can pick from all of the technologies together, not just the ones that are flagged as part of the RPS. And so that's what this new electric output allocated freely is doing. It's just allocating any residual demand to all of the technologies based on their cost. We do account for technical limitations on the amount of deployment. So you can see there's a maximum new electricity output buildable. And so that prevents the model from deploying more than what's technically feasible. Though I'll admit that in practice, we basically never hit that constraint. Summing everything up then gets us the total new allocated output. So the total megawatt hours that have been allocated. We then divide by capacity factors to get us capacity. And then lastly, this just adds in the policy mandated capacity. And that's the total new generation capacity to meet energy need. Eob, I'll come back to your question in a minute. But I mentioned there's also, so we have enough generation capacity to meet energy need, but we also have to make sure that the model can meet peak demand. So to do that, we start by looking at what is the peak power need. And we do that seasonally. So we look at summer and winter, and we use equipment load factors by sector. So each sector, and in some cases, even end uses within a sector, gets an equipment load factor, which represents the percentage demand in a given hour relative to the total annual demand for that resource. So you can imagine these numbers are small. They're going to be less than 1% because there's 8760 hours, but they would be highest for in the years, for example, for cooling, it's going to be mostly in the summer. And so these equipment load factors allow us to translate annual electricity demand within each sector, and in some cases by technology within each sector, to the peak demand by season. And so that's what's being calculated here. We then add a reserve margin. So power markets usually have a reserve margin requirement. That means they have to maintain at least some buffer, usually around 15% on top of what the anticipated peak demand is. That's what's here. And then we adjust that value to account for technologies that reduce peak demand. So that would include, for example, storage and demand response. If electric vehicles are able to provide electricity back to the grid or to be flexibly charged, that can be handled here as well. And then finally, if a region has transmission capacity that can be used to import electricity as needed during peak times, we adjust that here. And so when we're done with that, we get peak power demand after storage and demand response, but it also includes all these other things here. And that's the total peak power demand that needs to be met in the model in the summer and winter seasons. The next thing we do is calculate whether or not we need to meet new peaker capacity. Sorry, whether or not we need to build a new peaker capacity. So we have the total capacity before new peaker plants. We then have something called a peak time capacity factor. So this again is a way of trying to get at the fact the model is an annual average model and not an hourly model. But this is the capacity factor of each resource in summer and winter during the hour of peak demand. And what that tells us is in that hour of peak demand, what is the potential output of all the power plants on the system? If that number is less than peak power demand after storage and demand response, which we just calculated here, then that tells us we need to build more peaker plants to be able to meet peak demand. So right here is the peak power demand to be met by season. The model then determines which of those is greater. So if we need more peaking demand in winter, it will select that versus summer. And then it goes through an allocation step here, kind of like we just looked like, where it allocates that demand to new peaker plants. And this time, only plants that are flagged as peakers actually get built here. So kind of like the renewable portfolio standard, we have a toggle here for whether or not a plant is a peaker plant. And then at the very end here, we sum up both the new peaker capacity that's allocated and the new generation capacity to meet energy need. And then we do something where we divide by the minimum plant size. So sometimes you have kind of an awkward unit. For example, maybe the model allocated 2 megawatts of a nuclear plant. Well, most nuclear plants are at least 500 to 1,000 megawatts, just because you're not going to build a 2 megawatt nuclear plant. So we round down after dividing by the minimum power plant capacity to get the new generation capacity in aggregate. We need to answer a couple of questions, then I'm going to turn it over to Megan to jump in and carry us forward. So the price assumption for the resource generation type, where's that? So we're going to go over that next. It's in the next row. And it's based on multiple factors. So it includes construction costs, different types of O&M, fuel, subsidies, variable costs, and so on. Does the model decide between text where costs are the same? So it's if the costs are literally identical, then you would get exactly proportional megawatt hours being allocated to each. And then when you divide by the capacity factors, you would get different capacity amounts. In practice, though, the costs, while they may be close, they're almost never kind of perfectly overlapping. But the graphic that I showed here, this gives you an idea. You know, if the solar graph perfectly overlapped with the wind graph, the total curve would look different, and the model would still fill to meet the total curve, but it would fill in such a way that you got a proportional amount of wind and solar. Sure. Okay. With that, I'm going to turn it back over to Megan to keep us going.
Yes, thanks for giving me that little break to stop talking for a bit, Robbie, and eat some food. Appreciate it. I'll take over. All right. Okay. So, oh, I'm still on the buildings page. Let me switch over to electricity. So we just went through decisions on which plants to build. But an important part of that is the tracking the costs of the different plants. So we just got a question about where are those costs tracked. This is in the second, kind of the next row down from the row we just went through up here. Here we are calculating the annualized cost per unit output for new capacity. You can think of as an LCOE, or levelized cost of energy, which is that mean cost that we just saw in the graph, so the peak of those resource curves. So just to walk through how we calculate those annualized costs. So we start by reading in data on the construction costs for each power plant type here in the CCAMC. So this is a pretty important input data variable that needs to be customized for each region. And as part of that, we're tracking both what we call the hard costs and the soft costs. So hard costs are things like the actual construction and the materials of the plant. And soft costs might be things like the land that the power plant is built on and permitting costs. And we track those separately because the model applies endogenous learning for a few key technologies. I think we're going to cover the endogenous learning page tomorrow, but what that is simply is that for certain key technologies that are maybe earlier on the learning or deployment curve, the faster that you deploy that technology, the more learning by doing there is, and the faster those costs come down. So if you have a policy package that deploys a lot of wind and solar, the costs for wind and solar, we would expect those to fall a little bit faster than they would in the business as usual case. And we apply that endogenous learning just to the hard costs, not the soft costs, since those don't really change quite as much. So that's just keeping track of that endogenous learning and adjusting the costs due to that. And then there are a couple policies that can affect the cost of new resources as well. Again, we have this research and development piece that you can choose to apply to bring down costs faster. We can also look at a subsidy for capacity construction. So this would be a subsidy as a percentage of the construction costs of a new power plant. So add that up and track them. And we now want to turn those construction costs into annualized construction costs. So we have the generation capacity lifetimes of different power plant types. And we can then annualize those construction costs. And then we want to add in other annual costs that there might be. So we have input data on both annual fixed and variable O&M costs. Add those into the model, and also, of course, the fuel costs. So this is input data being read in from another page, but we have heat rate by power plant type, so the efficiencies of different power plant types, how much fuel they need to burn to produce a BTU of electricity, and we have the fuel costs for different fuel types. So that gives us our annual fuel costs. And then finally, that gives us cost per unit new electricity output in dollars per megawatt hour. And we can add in one more policy lever, which is a subsidy per unit generation. So sometimes instead of having, this would be equivalent to the production tax credit, the PTC in the US. We have $1 per megawatt subsidy, add that in, your total cost per unit new electricity output. And this is what's being fed into that logic function to make decisions on which new power plants to deploy. We also calculate a similar variable, not looking at construction costs, but just the fuel variable O&M and fixed O&M costs per unit output that we're going to use below in the dispatch calculations. But this is constructed with the same type of logic as that other variable over here. And now we get into a section of the code that is looking at retirements. So there are a few different ways retirements are handled in the model. This is looking at potential capacity that is retired early for economic reasons. So we have a bit of a clever approach to, for how to do this in the model without having to track power plants at the plant level. So here you see parallel code that is computing the mean cost of electricity for both the policy case and the business as usual case. So we know how much electricity is being generated by each type of power plant. We have a 1-year time delay in order to avoid circularity here. So we're looking at last year's electricity generation by type. We have those dispatch costs that we just calculated in that last block of code, and that can give us the average cost of electricity produced by the grid. For each power plant, we're going to look at the difference in their dispatch costs relative to the mean electricity costs. So for wind and solar resources with 0 or very low dispatch costs, that will be a negative number. For plants that are more expensive than the mean, like coal plants, that's going to be a positive number. And then we're looking at how those differences in costs relative to the mean change between the policy case and the BAU case. So if a plant type is becoming more uneconomic, so if you're having more wind and solar come on, which is driving down the mean cost of electricity, meaning that coal plants are becoming more uneconomic relative to the mean, that's going to incentivize some early coal retirements. And we come up with an elasticity value, which is the annual retirement per unit increase in relative cost. We calibrate this using some historical data. So for the US, we're using some data from the Annual Energy Outlook, some of their side cases that look at what different power plant types retire in different scenarios with higher fuel prices, and use that paired with this change in relative cost to come up with the amount of economically induced power plant retirements. We also can account for the fact that we might want to kind of manually specify in the model that a certain amount of capacity is retiring. You might have already planned retirements that you know you're accounting for, or maybe you want to look at a situation where you know, you're saying we think coal is going to retire early because we're going to put on some air quality standards that would require polluting power plants to shut down. That's a policy lever that we can account for here and add some additional capacity that might be retired early. And then we come to another stock and flow section where we're tracking the capital stock of each power plant type. So we know what the new generation capacity is, which we calculated above and Robbie walked us through. We've calculated our retiring generation capacity, and we know what our generation capacity was last year. All right. We now get to a little bit of a different topic. The electricity sector, because there's so much going on, it isn't quite as logical a flow as we had going through the industry and the building sectors, so it jumps around a little bit. But here's where we're calculating those flexibility points that Robbie mentioned. And so again, the flexibility points are really an abstraction to account for resources that provide flexibility to the grid, like battery storage or peaker plants and so on, and how those are connected to the grid through transmission. And if we don't have enough flexibility points, as we call them, you start to see curtailment of wind and solar. So this is really just tracking the available flexibility points we have from different resource types. And this is paired with input data from a study from a national lab that kind of looked at this flexibility point abstraction to determine how much flexibility different resources can provide to the grid. So this is tracking how many peaker plants we have on the grid and the amount of flexibility that peaker plants provide to give us our flexibility point from flexibility points from peaker plants. We do the same with grid battery storage. We also have a policy that allows us to turn on additional battery storage and look at a case where we're deploying more than in the business as usual case. And the new version of the electricity sector that we're working on, we will allow battery storage to be deployed endogenously based on if it's cost effective to do so. But in this version of the model, just important to note that the EPS is not going to automatically deploy storage in a situation where you're deploying a lot of wind and solar. This is a user-driven setting if you want to put on more storage beyond what happens in the business as usual case. We also track flexibility from pumped hydro plants, from demand response. Again, we have a policy setting where you can turn on more demand response, and that is specified as a fraction of what we see as the demand response potential, which is read as input data. Transmission from regions across the model border. So in the US, this would be imports from Canada and Mexico. And then flexibility points from electric vehicles if you are allowing electric vehicles to supply electricity back to the grid in times of peak demand. So this is adding all of that up to give us a total number of flexibility points. And then we connect those flexibility points to the grid through this additional abstraction called transmission connectivity coefficient. So in a case where you had unlimited transmission that connect, a solar plant in Florida to Washington State, you would have a transmission connectivity coefficient of 1. If you had 0 transmission, so nothing was connected, you'd have a value of 0. In real life, this is going to be a value in between 0 and 1, and we come up with this value based on calibration. So we can calibrate this based on historical data on curtailment based on varying levels of transmission. So this transmission connectivity coefficient is multiplied by the number of total flexibility points available to give us an amount of usable flexibility points. And you also have a policy lever that allows you to increase the amount of transmission. So as you increase transmission, you increase that transmission connectivity coefficient, meaning more flexibility is available. That's flexibility point system, which again will be going away once we transition to an hourly dispatch mechanism in the newer version of the model. And before we get down to dispatch, this is now moving down to the last row of calculations here on the electricity page. There are a few other kind of minor parts to point out. I'll maybe go a little bit faster on these. One is calculating the maximum buildable output. So this isn't referring to maximum buildable in a given year, just total cumulative maximum output. So we have input data to account for that. This is looking at things like a region may have limited hydro availability because there are already dams in most of the rivers. And so even if hydro were really cheap to build, you would reach a ceiling once you kind of maxed out that potential. So we are accounting for that here. For other resource types, we generally don't ever hit any kind of ceiling that we set for that, just because there's quite a lot of availability. And then we also have a policy lever where you can ban power plants of a certain type if you want. So you could say no new coal plants are going to be built in this scenario due to air quality standards or something like that. And that would disallow that plant type from being built. And this maximum buildable output is accounted for in those capacity allocation decisions that we covered above. And then finally, this is one other little piece that fed into the capital stock tracking that we had above. I think I just didn't point it out, is fuel type shifting and retrofitting. So this does a similar thing to what we looked at above, where we're tracking the change in costs. And this is saying, okay, if the fuel costs for, say, coal are going up, given elasticities that we're reading in through input data based on historical rates of retrofitting, would any of those coal plants be retrofit to a natural gas plant? And so that's what this is doing here in calculating an amount of electricity generation capacity shifted from coal to gas. Add that into the capital stock calculations that we had been doing above, and that gives us total electricity generation capacity here in orange. All right, the last part of this is really dispatch. And as Robbie mentioned, we do this in two systems: guaranteed dispatch and least cost dispatch. So first I'll touch on guaranteed dispatch. And this is used, again, really more in countries maybe like China, where the government has a little bit more of a say in what plants are dispatched, rather than a system like the US, where things are determined more through least cost. So you might want to say, okay, I want to guarantee a certain percentage of a given power plant type will be dispatched. And you can set that through input data here, both the BAU amount of guaranteed dispatch and then how much guaranteed dispatch you want in a policy scenario. And this is just a Boolean lever if you want to use the BAU guaranteed dispatch settings or your policy specified dispatch settings. And then we have these dispatch priorities. This is just for the off chance that maybe you set so much guaranteed dispatch that it exceeds the total amount of demand, and the model just needs to know then which ones to actually guarantee so that you're not in a case where you're over dispatching. And it will dispatch the percentage of available electricity. And that available electricity is determined by how much capacity is on the grid and the capacity factors of those given plant types. Now we also have, you can set through input data whether power plant types are bidding at their peak capacity factor or their expected capacity factor. So peak capacity factor for fossil plants, for example, you would expect their peak capacity factor to be at or near 1, because they can run near their full capacity for parts of the year. For wind and solar, the capacity factor is determined more by the resource availability And so you would have those plants bid at their expected capacity factors, which is what we read in as kind of the average annual capacity factors for a resource type. So that amount of available electricity output by plant is multiplied by the guaranteed dispatch settings. And then finally, just a note, we also guarantee dispatch for peaker plants. So we assume that in order to meet peak demand, those peaker plants are running at the capacity factors that are read in through input data. In the newer version of the model we're developing, we won't have a need to make that assumption because we can actually calculate the demand in every given hour and therefore how much peaker plants need to run. But just to point out that the peakers are handled through the guaranteed dispatch mechanism for now. So once you have calculated how much guaranteed dispatch you have, you can calculate how much demand there is to satisfy after guaranteed dispatch. And that's all going to be met through least cost. So we have the total potential electricity output by type after guaranteed dispatch, which again is determined by how much capacity you have and the capacity factors of those different plant types. And then this uses a similar type of algorithm to the logit exponent, but we use what's called Vensim's allocate available function. We do that because it's a little bit different in this setup because we know exactly how much potential electricity output is available for each plant type, rather than a case where you're looking at potentially what to build where there might not be a limit on how much coal capacity you could add in a given year. And this allocate available function follows that same concept of setting up resource curves with the average dispatch cost and then a normalized standard deviation of dispatch costs to set up those resource curves, and then filling in dispatch based on which costs or which plants are most economic to dispatch. And that leaves us with our amount of electricity dispatched by least cost. Now to add everything up, we take the amount of electricity dispatched by least cost that we just calculated, the amount of guaranteed dispatch that we have to give us total electricity generation by type. And then knowing that, we also have our input data on heat rates for different power plant types, so their efficiencies, the pollutant emissions intensities by power plant type, and that can give us our electricity sector pollutant emissions, so going from generation to emissions. We have a couple control levers here to just affect how we want to report out emissions based on whether we want to include emissions from exported or from imported electricity. So some regions in their greenhouse gas inventories choose to report in their electricity sector emissions, the emissions from imported electricity. Some regions exclude those, so we give users the ability to toggle those on and off. And then finally, we also account for any emissions from carbon capture and sequestration equipment that might be running in the electricity sector. Add that in for our total electricity sector pollutant emissions. This very last set of outputs here on the electricity page aren't necessarily integral parts of the calculation flow. They're just adding up useful totals or things that users might want to reference. So you can see there's a lot of calculations for these orange variables of interest. This might be things like just calculating the total amount of curtailed electricity we have in any given year, what the actual achieved capacity factors are for different plant types and how that compares to the expected capacity factors that we read in as input data. And we also have kind of these supplemental variables that we've calculated here for water withdrawals and usage by different power plant types. So we report those as output graphs as of interest as well. All right. So that takes us through the electricity sector, and I think we have some time for questions before moving on to our last sector of the day.
Hey, this is Jason. I just have a question about like overall calculating costs. I'm sorry if I missed this, but is this accounting for costs related to additional transmission and distribution builds? Or like how does it do that?
Yeah, so we'll get into a little bit more detail on this in the cash flow sections tomorrow. But as I mentioned, for each of these main pages, we have a separate cash flow tab. And you can see there's sections for kind of different technologies or things we want to track. We have changes in fuel costs for the electricity sector, changes in power plant construction costs, demand cost, storage cost, transmission costs, etc. The transmission and storage costs, we track them separately since the amount of transmission and storage built are based on these kind of separately defined policy settings. So I mentioned we have amount of storage that's built in our business as usual case, and then you can build more storage by specifying it through a policy lever, but the model isn't going to choose to deploy more storage on its own unless it's set through this policy lever for now. So we kind of separately track the construction costs and the operation and maintenance costs and the fuel costs of each power plant type, and then separately calculate storage costs, separately calculate transmissions costs, and the cost of all these kind of other sources of flexibility that are tracked separately here.
Okay, thank you.
Hi, I just have a quick question about, so when you were talking about calculating how to determine which kind of power plants will be built in the next year, you said that you were kind of comparing the average cost of each kind of technologies. And I was wondering, because in the US, for some idling power plants, they receive capacity payment. And also for the renewables, like some renewables, we have to consider about the transmission cost. Did you take into account of those kind of costs?
So in this version of the model, those aren't explicitly tracked. In the system that we're moving toward, we actually are going to have separately calculated capacity payments, as well as we think we're going to handle transmission costs through kind of a dollar per megawatt adder for different power plant types. But for now, no, those transmission costs, again, are calculated separately since we're really tracking transmission through a different lever, and that we're not varying the amount of transmission costs per by power plant type, like for wind and solar. So these costs we're tracking here really are the construction costs, the fuel costs, and any operation and maintenance costs.
I'm wondering, it seems like you do new capacity based on some assumed utilization rate. And then there's the dispatch. And I guess I'm wondering whether in the same sort of time step, you can get a situation where the least cost, let's say, is wind. So you deploy a fair amount of wind, but then you've guaranteed solar dispatch. And therefore, like, you get new capacity that's just not used, like kind of this unintuitive situation.
Let me parse that out. I don't think generally come across that type of issue due to time delays we have built in. Trying to think of where exactly to point to for that. This is something I might want to get back to you on tomorrow, just to make sure that I kind of have my head straight on this one, if that's all right.
Okay, well then, maybe I can just follow up with potentially a more straightforward question, because you, in the very last, I'll call it pane of the model, that section, you compare utilization rates. It's kind of related to the last question, but you compare utilization rates. And I guess I'm wondering, is there a feedback to the team utilization rates and the next round of investment? Because it seems like if a technology is not being utilized, maybe it was overbuilt or something, then you shouldn't build more of that. And maybe it is a situation where there's guaranteed dispatch of other generation technologies.
We really don't use the guaranteed dispatch in too many cases in the US. We're, for example, just looking at least cost dispatch, where you tend to see a mismatch between the actual utilization rates and the expected are, like if you see a big swing in fuel costs, like maybe you put on a carbon tax and your business as usual expected capacity factors weren't accounting for that. You might see gas plants dispatching at more than their expected capacity factor and coal dispatching at less than its expected capacity factor. And in a case like that, you're not going to be building more coal plants. So those kind of go hand in hand. Does that kind of answer your question?
That does make sense. Yeah, but it is I guess it would be this one that's called achieved capacity factors. Are those fed into the next time step as part of the investment decision?
The achieved capacity factors are we're going off of the expected capacity factors when looking at how much available output we have, not the achieved.
Okay, thanks.
I do see another question in here about validating the model. So calibration is definitely important. In the electricity sector, I think I mentioned in the comments for calibration of those logit exponents and share weights, we're definitely looking at calibrating to historical data to make sure that our start year dispatch and our deployment is looking good. And we do look to other models to kind of calibrate our projections against what other models are getting, looking to more detailed capacity expansion models, like looking at reads outputs, for example, to make sure that both a business as usual case and in a policy scenario, we're getting results that are relatively in step with what other more electricity focused models are finding.
Okay, thanks.
Yeah. I might, just in the interest of time, since we still have transportation to get through and have 40 minutes left, move us onto transportation. But we can certainly come back tomorrow with more questions, since I know electricity is one of the more complicated sections of the model. All right, gonna move us over to the transportation tab. All right, so this one is only one row of calculation flow to move us through rather than the multiple rows and columns we saw in the last one. But generally what we're going to do is we're going to look at our demand for cargo distance transported. So how much transportation demand there is in a given year. And then we're going to look at a few things that the model is going to use to make allocation decisions for what new vehicles are deployed, kind of similar to what we just did in the electricity sector. So that's going to depend on the fuel economy of vehicles, as well as the costs of those vehicles. And that's going to allow us to make a decision on what new vehicles are deployed. We're then going to track what the vehicle stock is based on new purchasing decisions and track what that means for the fleet average fuel economy. We're going to apply this big complicated section to meet any low carbon fuel standard that a user may set. And then finally, we're going to tally that all up and understand what the impacts to emissions and electricity demand are. So starting over here on the very left. All right. So we're first going to start by a few pieces of important input data. And just a note on terminology in the model. When we refer to start year cargo distance transported, start year in the EPS means the year before the first simulated year in the model. So in the US model, the first simulated year is the year 2020. So the start year data that we're feeding in is for the year 2019. So there will be a few variables in the input data folder of the model that say start year, and that's just an indicator that you want the year before the first simulated year. So we have the number of vehicles in the start year by vehicle type and vehicle technology. So as a recap, we're tracking passenger and freight modes of 6 different vehicle types. So you have light duty vehicles, heavy duty vehicles, aircraft, rail, ships, and motorbikes. We know the average vehicle loading, so how many passengers or how many freight tons these vehicles are carrying on average. We have an average annual distance traveled by each vehicle type. You multiply these 3 things together, and you get the amount of cargo distance transported, either in passenger miles or freight ton miles, if you're looking at freight vehicles. We then have another important piece of input data for cargo distance transported relative to the start year. So this just scales the demand for transportation in different vehicle types in each year of the model run. So generally we see transportation demand growing across the model run. We have a section to add in those macroeconomic feedback loops from the input-output model that we're going to cover tomorrow. And then we also have our first policy lever here, which is mode shifting, which I think we touched on briefly yesterday, but this is getting people out of their passenger cars and into public transit, or shifting the way that freight is transported. So you can track increases and decreases to the transportation demand for different modes, and give us an amount of cargo distance transported for each year. The one other thing that feeds into this is effects that changes in fuel costs might have on consumer behavior. So we have input data for an elasticity of demand for vehicle use with respect to fuel cost. So this is looking at that elasticity paired with the percentage change in fuel cost per unit cargo distance. So this is parallel computation for both the BAU case and the fuel case of what changes in costs for different fuel types are. So, you know, if you have gasoline costs going up, you might expect people to drive a little bit less, and that's going to be factored into this total transport demand. Now, similar to what we saw in the building sector, we want to separate separate out the demand that is from newly sold vehicles. So again, we have the share of cargo distance transported that is new this year, which is going to be determined by the average lifetime of different vehicles. And that gives us how much of that cargo distance demand is going to be from new vehicles. All right, so next step, we want to know the fuel economy of all these different vehicle types. So we have input data on expected new vehicle fuel economy. And then there are a few different things and policies that can affect that. One is the elasticity of new vehicle fuel economy with respect to fuel costs. So we know based on the past, if fuel costs are going up, auto manufacturers generally respond to consumer demand and you might have slightly more efficient vehicles. We also have a few policy levers that you can put on. Maybe the biggest of those is the percentage additional improvement of fuel economy standards this year. So applying more efficient or standards for more efficient vehicles. I mentioned this one yesterday. We can also apply a fee bait, which is a rebate for more efficient vehicles and a fee on less efficient vehicles. We have some historical data on what the impact has been of those types of programs on fuel economy. And then we again have our research and development piece showing up here where you can look at what research and development breakthroughs and efficiency of new vehicles might mean. Next, we want to calculate the net present value of lifetime vehicle costs. So like we use the LCOE in the electricity sector to make decisions on what new power plants are deployed. Here we're going to use the NPV of lifetime vehicle costs to make that similar type of decision. So first, we want to know what is the cost of a new vehicle, the upfront cost that you would pay. So that's in this input data here. And similar to the electricity sector, again, we can apply endogenous learning. So for electric vehicles, if you have policies that incentivize new electric vehicles, those costs are going to come down faster than they would in a business as usual case. And we want to apply that endogenous learning to the battery of the electric vehicle. So we separate out here the costs, the portion of the vehicle costs that are from the battery versus from the other components, and apply endogenous learning to the batteries. So that gives us our new vehicle price after endogenous EV learning. We have another elasticity we can account for here, which is the elasticity of vehicle price with respect to fuel economy. So if there are really stringent fuel economy standards, we know that that can increase the cost to produce a vehicle. So we account for that here. Another R&D policy to look at R&D breakthroughs and capital costs if you want to apply those. And then you can also offer subsidies for vehicles. So we have the option for users to set an EV subsidy this year, which is set as a percentage of the overall vehicle costs. Then one last piece here, this isn't accounted for in the cash flows because it's not a real price. This is what we call a shadow cost that we include here that just impacts the consumer purchasing decisions. But this is a way to reflect non-monetary barriers that some consumers perceive for electric vehicles due to range anxiety and charging concerns. So we use some academic literature to come up with the perceived shadow cost of electric vehicles for some consumers. And then through a policy lever, you can actually reduce that range anxiety and charging time to look at how that would affect vehicle sales. Then the other component, besides just the upfront price of the car, is of course all the fuel and operation and maintenance expenditures, which are tracked up here. So we already know the fuel economy of new vehicles. We know the price of different fuels, and that can allow us to calculate based on vehicle loading and average distance traveled, what the annual fuel expenditures are for a vehicle. We then have input data on a few different things like annual maintenance costs, insurance, parking, and licensing and registration costs to add those into the total. And then we know the average vehicle lifetime, so we can count up all the years of fuel expenditures and so on. And then we apply a discount rate to come up with the net present value of all of those costs. So adding that all together, we have our NPV of lifetime vehicle costs. And this is what's going to be fed in to our next section here, which is used to calculate the number of new vehicles. So we have our new cargo distance transported, which we calculated earlier based on the lifetime of different vehicles and how much transportation demand there is in each year. That can allow us to calculate the new number of vehicles demanded, since we know, again, the loading of different vehicles and how much they travel on average in a given year. And then here we see another logit function applied. So this is very similar to the electricity sector, the same type of calculation, where we have a logit exponent and share weights. And these we use calibration to help determine the right values for these. We have the NPV of lifetime vehicle costs, and that is going to allow us to allocate for each vehicle type the demand for new vehicles into the different vehicle technologies that we track. So we can track up to 7 different vehicle technologies for each vehicle type, which includes gasoline vehicles, diesel, electric, plug-in hybrid, hydrogen, and natural gas, I believe, are the ones that we track. There are a couple other policies that can affect which vehicles get purchased. This is one we're not actually using in the US model right now, but we have the ability to put input data in the future for this, which is what the effect of EV charger deployment would be on the market share of electric vehicles. And we also have sales standards. So you can specify amount or percentage of vehicle sales in a given year that need to be electric vehicles or hydrogen vehicles. And that will kind of override the cost-based deployment. If you're saying 100% of electric vehicles or 100% of vehicle sales need to be electric next year, the model will just apply that directly rather than doing a cost-based allocation. So now we have the total number of new vehicles of each technology type we are selling in a given year. We just want to keep track of the vehicle stock. So we know our number of vehicles last year. We now know the number of new vehicles. And we can calculate the number of retiring vehicles based on the average vehicle lifetime. And that gives us our number of vehicles in this year. Now, in order to go from number of vehicles to emissions, we need to keep track of the average fuel economy of the entire fleet. So this is just a section of the calculation flow that accounts for that. So you have new vehicle fuel economy, which we calculated earlier. We have some input data on historical new vehicle fuel economy. So for those model years that are already on the road at the start of the model run, we have data on what their historical fuel economy has been. This all allows us to calculate a percentage difference in new vehicles fuel economy versus the fleet average, and for retiring vehicles versus the fleet average. So we can come up with the new vehicles contribution to the fleet average fuel economy. Same for retiring vehicles. That gives us an overall percentage change in the fleet average fuel economy in each year. And that's what we need to tally up emissions at the end of this. But before we get to emissions, there's one other big section here for the low carbon fuel standard. So I'm going to walk through this. This is a policy that can either be in the business as usual case. You can set a BAU LCFS requirement. You can also turn on an additional LCFS requirement through a policy lever. And what this is it sets a standard for a reduction in the carbon intensity of transportation fuels that a region needs to achieve. So in order to calculate this, we need to know a few things. One is the BAU percentage of fuels that are used by each vehicle technology. So for something like a battery electric vehicle, that's pretty straightforward. It uses 100% electricity. For gasoline cars, though, you would expect mostly gasoline, but we know that there's some ethanol blended into our gasoline, and so it's some high percentage gasoline and a smaller percentage biofuels. And we know the fuel economy of different vehicles, so we know how much transportation sector fuel of each type is used in the absence of an LCFS, a low carbon fuel standard. We then need to account for the fact that all vehicles might not be subject to the LCFS. So for example, in California, which has a standard, the aviation sector does not apply. And so we would exclude fuels used from the aviation sector in our calculations here. We then just do kind of an accounting adjustment here to account for the fact that electric vehicles are more efficient than internal combustion engines. And so if we want to compare the amount of fuels that would be used kind of on an apples to apples basis, we need to make that electric efficiency adjustment to account for the fact if that electric vehicle were actually a gasoline vehicle, it would be using more fuel on a BTU basis. And then we're looking at the carbon intensity ratios of different transportation fuels. So biofuels are much less carbon intensive than gasoline and diesel. Natural gas has a slightly lower intensity than gasoline and diesel. Electricity has a value of 0 here for accounting purposes. We can add up based on the carbon intensity ratios of all those transportation fuels and how much fuel is being used, what our total amount of carbon-free energy is before we apply any type of LCFS. We can also calculate how far in our business as usual we come to meeting the LCFS requirements. So we can look at, okay, based on how much ethanol we already have blended into our fuels, based on how many electric vehicles we have on the road, how close are we to meeting that LCFS requirement? So that's what's calculated here. Here we're keeping track of what our business as usual LCFS requirements are. Any additional LCFS requirements we layer on through our policy lever to understand what the required percentage is, and if we need to then shift more fuels to lower carbon fuels in order to meet the requirement. Now, an important note about how the model handles this policy. So this LCFS policy is going to shift fuels within a given vehicle type. So it can shift from gasoline to biofuels, for example, in a given vehicle type, but it's not going to affect the purchasing decisions. So we already calculated the number of new vehicles of each type and technology, and this policy doesn't affect that. So if you set a high LCFS, it's not necessarily going to drive additional electric vehicle deployment in the model. It's going to try to meet that LCFS by shifting fuels within existing vehicles, so shifting from gasoline or diesel to biofuels. If you have a bunch of electric vehicles, due to either economic deployment or other policies you put on, like an EV sales standard, those will contribute to meeting the LCFS, but this LCFS policy on its own is not going to drive those deployments. It's just going to shift between different types of fuels, given what fuel types a particular engine can burn. So we have input data on the maximum percentage of each fuel usable by vehicle technology. So this number is going to be higher for things like biofuel consumption in heavy duty vehicles, because we have drop-in biofuels that can get close to 100% of the fuel required to run those vehicles. In aviation or shipping, for example, we might set a lower number to account for the fact that we don't expect in the near term, at least, to be able to run those fleets entirely on sustainable fuels. This then steps through based on how much fuel can be used by each vehicle type, how much we can shift, and then kind of does that proportionally based on the potential for shifting. So if we have a lot of potential for biofuel shifting in HDVs, because we have a high value for this maximum percentage variable, we have a lot of HDVs on the road, we'll see most of our shifting in order to meet the LCFS happening for heavy duty vehicles as opposed to other vehicle types like shipping. So I won't step through this in more detail here, but that's essentially what's happening in that part of the calculation flow. And that's done proportionally in order to meet whatever LCFS requirements you've set over here. We now want to kind of undo some of the adjustments that we made. So we undo that electric efficiency adjustment that we did earlier. And that gives us our total amount of transportation sector fuel used by fuel type and by vehicle type and by vehicle technology here. And finally, putting that together at the end for emissions and electricity use. So we know our fleet average fuel economy, which we calculated earlier. We know our business as usual fleet average fuel economy, and we can calculate then a percentage change in fuel economy as a result of all the policies in our package. We also have pollutant emissions intensities for all the different vehicle types here. And this is one last policy lever that we can set, which is percentage reduction of separately regulated pollutants this year. So this is looking at not CO2 tailpipe emissions, but emissions of some of the other pollutants that we track that might be regulated because they have impacts on human health. These separately regulated pollutants are tracked separately from the fuel economy calculations that we had earlier, because the types of technologies that you can implement to cut down on pollution of non-CO2 emissions might look different from tracking CO2 tailpipe emissions. Sorry, it's been a little bit since I visited this section of the code. So basically, we're looking at the percentage change in fuel economy, the percentage change in these separately regulated pollutants, the pollutant emissions intensities for each of those to give us total transportation pollutant emissions. And we can sum those up here. And we separately break out the electricity demand from the rest of the fuel demand here in order to feed this into the electricity sector. All right. Sorry, that was a little bit of me reminding myself what's happening in this last section here. But I think that's really the last piece of the transportation sector. So we've got about 15 minutes left here just to touch on questions from transportation or jumping back to other things that we've covered today. I see a few things in the chat. Good point on different classes of trucks. So we have light duty vehicles and heavy duty vehicles tracked in the model. For freight, light duty vehicles, we have classed as light and light medium. So class, I think 2B through class 6. And then our heavy duty vehicles are classes 7 through 8. If we're doing more transportation improvements in the future, we're thinking about disaggregating those even further to separately break out light, medium, and heavy duty. But that's how we have those broken down right now. Although there is flexibility in input data to classify different vehicle types together, however it makes the most sense for a given region. Couple other questions here. So for fleet-wide fuel economy, so we have separate fuel economies tracked for each vehicle type in terms of BTU's energy required per passenger mile or per freight ton mile. So yes, we're separately tracking how much what the gasoline demand is for gasoline vehicles, what the diesel demand is for diesel vehicles, the electricity demand is for electric vehicles, and so on. And so, yes, as you have more ZEVs come online, that does reduce fleet-wide fuel economy.
So, yeah, so basically what I wish to ask is, if you have a vehicle emission standard in place, does that increase
I
the
see.
uptake of Z? Yeah.
I see. So we actually have a piece of input data that determines which vehicles are subject to fuel economy standards, and they're set at the vehicle technology level. So we can apply fuel economy standards for gasoline vehicles and diesel vehicles, but we don't right now have the ability to set just an economy-wide like CO2 intensity standard, and then the model determines how to meet that through a combination of electric vehicles and efficiency improvement in ICE vehicles. So the efficiency improvements that you apply are really just going into the gasoline and diesel vehicles and not incentivizing more electric vehicles to come online.
Sure.
We also have, what is the foresight for the MPV calculation?
Yeah. So in the technology choice algorithm, you mentioned that there's like an NPV calculation that affects that. So for how many years ahead does the decision maker look?
Yeah, so we do account for all the years of a vehicle lifetime, but you can change the vehicle buyer discount rate here for how heavily purchasers are looking towards those later out years. So it's by changing this input data on the vehicle buyer discount rate that you can change those assumptions.
Sure. What is the default discount rate?
I believe, let's see, for transportation. Just opening up this file. %15%.
Okay.
I've got a couple questions.
Yeah.
First, Megan, thanks for such a long day of trudging through this. It's you've done great work, you and Jeff and everyone on the team. So this is a huge effort, and I know going through it all and throwing it out and explaining it can be hard. So great work. I have one question that's kind of, I guess I have two that are a little bit just around transport and one that's more broad. One is, I appreciated the range anxiety variable. And I was like, oh, that makes a lot of sense. So I like the idea of having a softer variable for sort of the nebulous people are afraid of a new technology. But then later in the next segment, you had the effect of EV chargers on adoption as coming down from the top. And I was wondering if that was kind of double counting the same thing. Like, to me, one way
Yeah.
range anxiety will go away is when the network is, charging networks everywhere.
Yeah, so this is, I mentioned we're not actually using this in the US right now. It's kind of an artifact of something we put in and then decided this is really better handled through that shadow cost piece or through calibrating share weights, for example, on the logit function. So we have this filled in with a zero effect. Basically, we've set it up here for in the future if we want to. If you have data on the effect of, for this many chargers you add per 1,000 people or something like that, there's an X percentage increase in the market share. You can apply that here. We were finding one that could lead to really runaway deployment of electric vehicles. So that historical data used to fill in this variable was probably pretty accurate at lower penetrations of EV chargers. But if you extend that out to a really high level charger deployment, you wouldn't necessarily expect that on its own to drive, 100% of new vehicle sales as electric, which is what you could do if you set this high enough. So we were finding it wasn't quite realistic. And then to your point, representing this through a shadow variable is probably a better way to do it. So this is just really an artifact here if we ever want to add it back in, where we're using values of 0. So this is like a 0 impact in the model right now.
Okay. I don't think we need to go too far into this, but I guess in my head, I didn't think biofuels were particularly, when you did a life cycle analysis of ethanol, it wasn't particularly low carbon. But I don't know how, maybe that's what you're using, like what the EPA is saying or something else. But
yeah,
anyway.
We are using the EPA assumptions on the carbon intensity of biofuels right now and really not counting them. But through input data, you have the ability to set a different carbon intensity ratio if you want. So you can set this up to have a much kind of lower impact of biofuels towards achieving that LCFS if you would like to. And so there would be kind of a limited effect of the LCFS lever, because again, this isn't encouraging deployment of new electric vehicles on its own, just kind of accounting for how far the existing electric vehicles go towards meeting that standard and then shifting biofuels to meet the rest. So the lever wouldn't have as much impact if you did that, but definitely a fair point about the EPA assumptions versus other life cycle assessments of biofuels.
Thanks. And then my last question, I guess, is really broad, which is, I did a quick search and I don't, through the Venson file on it, but how is just population attributed or not attributed? I mean, I don't think there's a variable for population, although there's one that kind of related to this, but like, what's your approach to population, or just treat everything as, is that outside the model boundaries?
Yeah, population does come in for some of the input-output calculations, kind of determining employment and so on. But generally, because we are not building our own business as usual case in the model through population or GDP projections, we're taking in projections from other sources. Really, that kind of population driver piece of it is outside of the model. So we're more going off of in the US, where we're drawing in most of our energy service and transportation service demand from the annual energy outlook, going off of what EIA is assuming for how population is driving demand for new building consumption and transportation and so on.
So just in essence, is there a variable like per capita emissions? For instance, just at the end of the day, can you get something that says per capita emissions?
You can calculate it, but because we do read in like a population number, which we use in the input-output model. And so we do have, in some regions, we report like emissions per capita value. But that, because we take in input data from different sources for different sectors, there's not a guarantee that population is exactly the same between what we're reading in as our input data versus what was assumed in the AEO.
Okay, thanks.
Let's see. Other questions in the chat? I know that was just a note from Ian. Thank you. Any other questions in the last couple minutes we have?
Yeah, just to confirm, I mean, I would imagine probably not, but are you able to comment through your model on the technical feasibility of a very stringent policy? So as an example, some countries are asking for 100% ZEV mandate by 2035. And there are concerns that may or may not be possible because of the difficulty in ramping up critical minerals and so on. But I would imagine a model like this assumes that there is no such constraint.
Yes, you're right. We don't capture those types of constraints in this model. So it's really more of a user judgment call for how quickly you think you can ramp in a standard like that.
Sure, thanks.
All right, anything else? Okay, well, that takes us pretty much right up to the end of the hour. So I think we'll stop for today. I know we've covered a lot of content and a little bit more to do tomorrow. So thank you all for sticking with us, and hopefully this has been somewhat helpful.
Thanks very much, Megan.
All right, see you all tomorrow.